All right, everyone, you're seeing the results of doing an at-home haircut with clippers because all of the people who cut hair for a living are socially distancing. Continue. There, just turned off the, okay. So, let's get this set up. Get that. All right. If you do some reading on relativity outside of this textbook, if you read a little more widely on relativity, you're soon going to see the name Ernst Mach. Ernst Mach was a 19th century Austrian physicist and philosopher, and he also worked in a few other areas of science besides physics. He is most famous for this book, The Science of Mechanics, which was written in the late 19th century, and it's a history of mechanics. And it's a very insightful book. He basically goes from the ancient Greeks to the present and really delves deep into the assumptions behind every single thing in mechanics. And it influenced Einstein. It's actually just one little thing in there that influenced Einstein. The book is chock full of insight. It's also chock full of examples of him pushing incredibly hard on assumptions everywhere, most of which have nothing to do with relativity, but that's the thing he did. He pushed on assumptions. In reading, especially the first few chapters of it, will really force you to understand freshman mechanics better. If you can actually work through the examples that Ernst Mach presents and really understand what he's critiquing, you will really have freshman mechanics down. And then somewhere in there, he starts asking some questions about relative motion and pushes hard on the things that Galileo and Newton had to say about relative motion, and comes up with a principle that, frankly, I thought was crazy until I read a mid-20th century article on attempts to go beyond the general theory of relativity and the realization that Ernst Mach might be right. So, or at least that Ernst Mach is not obviously wrong. Anyway, I really, really, really recommend Ernst Mach, and I wish I had read him sooner. And with that, let's start talking about relativity again. Okay, so last time we established that time is different for different observers, that events that seem simultaneous in one reference frame might not be simultaneous in another. So what this means is that we're going to have to think very carefully about our definition of time. And it turns out that there are at least three perfectly reasonable concepts of time that we could define in relativity. And we're going to use these three concepts. One is called coordinate time. Now, coordinate time doesn't mean literally spatial coordinates, but it does mean just the time that...
Professor, are you sharing your screen?
Oh.
We can't see it.
Oh, sorry. Yeah. All right. There. Okay. And the chat was probably saying, yeah, I don't think screen sharing is on. Sorry about that. All right. So the first one is called coordinate time. And it would just be the time that some observer who's in an inertial reference frame measures between two events. Now, there's one very specific assumption there. This observer has to be in an inertial reference frame. But this observer does not have to be present at both events. Or more to the point, that observer could have clocks present at both events. You know, if the if the first event is that a train leaves New York, and the second event is that a train arrives in DC, there could be a detector in New York and a detector in DC, and those two detectors could be stationary with respect to each other. and they could measure the time between those two events. And although those are obviously two different observers, those observers share a reference frame in that those observers are stationary with respect to each other. All right, so that's coordinate time. And that's the time that we're more or less used to. The next one is called proper time, which is a terrible piece of terminology. I did not invent the word proper time. I hate that term, but it's what we're stuck with. And it's the time between two events that's measured by an observer or a clock that is present at both events. So this is different from the previous one, because in the previous one, you have one clock in New York, you have one clock in DC, and each of them measures the time of one of those two events, the departure from New York, the arrival in DC. Proper time, you've got a clock that's present at both events, the departure from New York and the arrival in DC. And I don't know why it's called proper time, but there are an infinite number of proper times, because there are many different ways for a clock to be present at both events. One way for a clock to be present at both events is to move between the two events at constant velocity, all right? And if that observer who is present at both events moves between them at constant velocity, they're in an inertial frame. But there's another way for that clock to be present at both events. That clock could take off from New York really, really fast, faster than the train, get to DC way ahead of the train, then just chill out in DC and wait. Is that observer in an inertial reference frame? Any guesses? Is that observer in an inertial reference frame? They take off from New York really, really fast. They get to DC before the train. Once they're in DC, they stop and wait. Well, ask yourself this question. Is that observer's velocity constant? First, they go really fast, then they stop and wait. So for part of this trip, their velocity was most definitely non-zero, or at least it was non-zero relative to many observers. Then for the second part of this series of events, the velocity is zero, or at least it's zero relative to many observers. So yeah, this observer is in a non-inertial reference frame. Their velocity changes. On the other hand, somebody who goes from New York to DC at constant velocity, they are an inertial observer. Now, what about somebody who goes at constant speed, but they go in an arc? Okay, so constant speed, but in an arc. Are they in an inertial reference frame? Anyone? Anyone? Bueller? Bueller? No? Well, is constant speed the same as constant velocity? No, because velocity is both speed and direction. The person going in an arc at constant speed is changing direction throughout their trip. So they are most definitely not an inertial observer. So every observer has their own proper time. If someone asks, what's the proper time between these two events? The first question you have to ask is, well, whose proper time? And I'm going to harp again and again on motion in an arc or motion in a circle, because a lot of experiments done in particle physics involve particles, charged particles, traveling in circular paths. It turns out to be really convenient to send charged particles around in a circle. It's a good way to speed them up before sending them slamming into a target and seeing what happens. Now, coordinate time was not unique either, because coordinate time, well, whose inertial reference frame? There are many inertial reference frames in which you could measure the time between two events. There are many moving observers who could be present at both events. But then there's the space-time interval. And the space-time interval is the closest thing we have to an absolute in relativity besides the speed of light, because it's the time, it's uniquely defined. The space-time interval is the time between two events measured by a clock that's present at both events, and that clock is inertial, meaning that it's moving at constant velocity. And if someone who's moving with that clock were to let go of an object, that object would not spontaneously speed up or slow down. All right, so the space-time interval is the time between two events measured by someone who's not accelerating yet is present at both events. And that's the one uniquely measured time. A way to think about this is to look at this diagram here, events A and B. The coordinate time between event A and B would be the difference between this position along the t-axis and this position along the t-axis. The space-time interval would be measured by a person who followed this trajectory between those two events. And a proper time would be measured by, say, well, anyone who was present at both events. This person here following the curved arc between those two events, that is one proper time. It's not the only proper time, it's a proper time. The space-time interval is also a proper time. It's the proper time measured by that person who moved at constant velocity between both events. It's also a coordinate time because that person who measures the space-time interval, they define an inertial reference frame. Their clocks are part of an inertial reference frame. So the space-time interval is a proper time. It is a coordinate time. But not every coordinate time is a space-time interval, and not every proper time is a space-time interval. Another way to think about it in geometry, and we're going to get to more geometry later this class, 2 points here. There are many paths in space that would get you from one point to the other. And so if I were to ask how long is a curve connecting these 2 points in space, the only correct answer is to come back with another question. Well, which curve are you talking about? If we ask what's the shortest distance between those two, well, it's uniquely defined. And that would be analogous to the space-time interval. And then finally, if I were to ask not what's the distance between these 2 points, but what is the difference in y-coordinates, well, it looks like this point is just slightly below that point. So that difference in y-coordinate would be roughly analogous to coordinate time. This shortest time would be roughly analogous to space-time interval, delta S. And this arbitrary path would be analogous to proper time, delta tau. Now, you can't push too hard on that analogy because it turns out that the space-time interval is the longest possible proper time, not the shortest possible proper time. But we'll get to that later. Any questions? Sometimes it's impossible to measure delta S, or at least it's impossible to measure a real value for delta S. If 2 things happen simultaneously, we could ask, well, how do we know what's simultaneous? If 2 things happen simultaneously in my reference frame, you know, if I'm sitting here giving my lecture and at the same instant on the other side of the globe, someone has illegally left their house to buy ice cream, okay, I can't be present at both events. So it's impossible for me to measure a space-time interval between them. All right, so let's actually try to calculate delta S, the space-time interval. Like I said, it's the time on the clock that is present at both events and travels between them simultaneously. Now, the way we're going to measure this time is we're going to talk about light bouncing back and forth between 2 mirrors. And that may seem like a rather strange clock. You're used to clocks looking like watches, or you're used to clocks that are just little digital readouts on an LCD screen. And those digital readouts come from the vibrations of some sort of quartz oscillator. But in fact, there's a very important category of clocks used all the time that really are just light bouncing between two mirrors. Atomic clocks really consist of light bouncing between two mirrors. The atom that's giving the atomic clock its name is an atom that has they've selected a very particular transition between two energy levels of that atom. And so they're looking at the light that's emitted or absorbed when the atom goes between those two energy levels. And they use that atom to fix the frequencies they're going to look at. And then they have that light bounce back and forth confined inside of a cavity. This is just like the standing waves that we've come back to repeatedly this semester. And so they've got light trapped in a cavity. It's the light absorbed and emitted by these atoms. And they're just counting the number of cycles of oscillations of that electromagnetic field. And they use these atomic clocks all the time. They're used in GPS. They're used as time and frequency standards that wind up actually getting used behind the scenes for time stamping a lot of transactions in the financial sector. And there's actually a lot of people who make good money really just working on the calibration of timing and frequency standards. So we're going to talk about two mirrors separated by some vertical distance h, light bouncing back and forth between them. And somebody's holding on to this pair of mirrors, and they're going to move at constant velocity from point A to point B. That's all they're going to do. They're going to just move steadily from point A to point B, holding these mirrors. And we've set things up so that in the time that, it takes them to go from A to B, the light makes a round trip, okay? So somebody is holding on to these mirrors, watching the light make a round trip. And it's very important that this is light traveling back and forth because the speed of light is one of the few things that everybody agrees on in relativity. All right, well, this person going from point A to point B, they measure the space-time interval because they're moving at constant velocity. They're present at event A when they depart and when the light starts traveling upward. They're present at event B when they arrive here and the light returns to the bottom mirror. And the time that that's going to take is just 2h over c, because 2h is the round trip distance. Distance divided by speed is the time elapsed. And in relativity units, or grown-up units, as physicists sometimes call them, c is 1. So this time is just 2h. Any questions on this idea? Even if it seems silly, even if it seems like a really nitpicky thing, ask it. Because this is subtle. Okay, somebody else, another inertial observer in a different reference frame. As far as they're concerned, the person who's moving from point A to point B, well, they just have the two mirrors with them the whole time, okay? So they see the light go up and down. They see the light just moving vertically. But someone else sees these two mirrors moving from left to right. So they see the light travel along a diagonal path up and to the right, and then a diagonal path down and to the right. Now, they must measure a different time between these two events because they see the light travel a much longer distance. And if these two observers have to agree on the speed of light, it's one of those few things in nature that doesn't change. It's one of those things that isn't just like your opinion, man, but really does follow some absolute rule. Then they must measure a different amount of time. Now, let's see here. The different amount of time that they must measure must be the distance traveled by the light divided by the speed of light. So that distance is c delta t, or just delta t in grown-up units. And that's got to be 2 times this hypotenuse. All right? Now, that hypotenuse is going to be the square root of h squared, the vertical distance, plus delta x squared over 4, because remember, the base of this triangle is not delta x, it's not the distance from A to B, it's half the distance from A to B. So we're going to square delta x over 2. And then we're going to multiply this whole thing by 2 because it travels this hypotenuse up and to the right and the same hypotenuse down and to the right. So when we put all that together, we get 2h squared plus delta x squared. So we get that delta t squared is equal to 2h squared plus delta x squared. And 2h, that's the space-time interval between these two events. So we get that delta t squared is delta s squared plus delta x squared, or delta t squared minus delta x squared is delta s squared. Now somebody must have a question, and I'm prepared to sit here and make it awkward until someone asks that question. Somebody must have a question on this. If you don't have any questions about relativity, then that means that you don't understand it. Because if you really understood relativity, you'd realize how weird it is. Somebody must have a question. Okay, is this graph a space-time diagram? No, this picture is not a space-time diagram because a space-time diagram has t on the vertical axis and x on the horizontal axis. This is just a picture in space. This is the y direction. This is just a direction in space, and this is another direction in space. So we're just watching light travel in space. We're not watching a space-time diagram. If it were a space-time diagram, I would have an axis that I would either label t or t prime. Other questions? Here's the thing. This is the same in all inertial reference frames. I made no assumptions about what this reference frame was. The only assumption I made is that whoever measured delta x and delta t saw this pair of mirrors move. That's the only assumption I made. But I didn't assume how fast they saw the mirrors move. I just assumed that they saw the mirrors move, and I assumed that they are in an inertial reference frame. That's it. I made no other assumptions. Okay? And so this should be true in any reference frame. If one person is walking at constant velocity from point A to point B and another person is just sitting on a park bench watching them move, well, that person on the park bench is in an inertial reference frame. If a third person is traveling at 0.999 times the speed of light, well, they're in an inertial reference frame. If yet another person is traveling at 0.999 times the speed of light in a different direction, they're also in an inertial reference frame. All of these people could be making observations. If somebody's moving alongside an electron at 0.6 times the speed of light, and we're going to learn later this semester, the electron microscopes often have electrons traveling that fast, they're also in an inertial reference frame. Any of these inertial reference frames are valid. They will all have different values of delta t. They'll all have different values of delta x. But whatever they measure is the time interval between when this person left point A and when they arrive at point B. And whatever they measure is that distance between point A and point B. These numbers could all be different, but delta t squared minus delta x squared, that is constant. Now I made an assumption here. I assumed that however much the observers might disagree on delta t or delta x, remember, according to the person moving with these mirrors, you're always at the origin of your own reference frame. As far as they're concerned, delta x was 0. You may be thinking, no, delta x isn't 0. I mean, they started off at point A, they arrived at point B. But remember, for them, you are always at your own origin. You have never in your life succeeded in walking away from yourself. Now, usually this is a point made by pop psychologists to say that the one constant in your life is you, no matter where you are, that's where you are. You can't escape yourself, yada, yada. But just in terms of measurement, you are always at your own origin. As far as this person holding the pair of mirrors is concerned, point A moved away from them. Point B moved towards them. They stayed still. So everybody disagrees on delta X and delta T, but I'm asserting that H is the same for all observers. And there's an argument in the textbook for that. I like this argument, so I'm going to walk through it with you. Suppose that the two observers disagreed on H, okay? So we got two people, and they're going to disagree on who's moving and who's standing still, but they've both got sticks, and they stand next to each other, and they agree when they're standing next to each other and not moving relative to each other that these sticks are the same length. And they put little paint nozzles and detectors on the sticks. And they set it up so that when this stick is in the immediate vicinity of another stick, because of some sensor on there, it will spray paint at the other stick. All right, now they agree on the length of these two sticks when they're standing still with respect to each other. But then one of them starts moving with respect to the other. One of them's me, one of them's you. All right? As far as I'm concerned, you're moving. And as far as you're concerned, I'm moving. Now, let's say that I think that the moving object gets shorter. We could do this the other way. We could say that I think that the moving object gets longer. It doesn't really matter. The same paradox will arise in either case. If I think that the moving object is shorter, then I think that your stick is shorter. So I think that your stick will get contracted, okay? I think it'll look like this. I think you'll be shorter, and I think your stick will be shorter. And your shorter stick will spray paint here and here to 2 points somewhere near the middle of my stick. Whereas my stick being longer, it'll spray paint, but that paint will go over the top of your stick and under the bottom of your stick. So I think that you're going to have paint on your hair and your feet, and I think that I'm going to have paint on these 2 points on my stick. Now here's the problem. The laws of physics have to be the same for all observers. So if I think that a stick that's perpendicular to our relative velocity gets shorter in a direction perpendicular to our relative velocity when it's moving, then you must think the same. So you must think that my stick gets shorter, okay? And if you think that my stick gets shorter, then you must think that I have paint on my hair and my feet, and that you have paint at 2 points near the middle of your stick. All right, so this is what we think. But now here's the thing about the laws of physics. The laws of physics, we can disagree on what we see while we're moving, but we have to agree on what we see once we slow down, one or both of us stops moving, we catch up with each other, and we stand still right next to each other. We have to agree on what's happening when we're standing still right next to each other. So we're going to have a paradox. If I look at you and say, you have hair, you have paint on your hair and paint on your shoes, and you look at me and say, no, I don't. You're the one who has it. Okay, we have to be able to agree on that. And right now we're getting paradoxes here. So in order to avoid paradoxes, we are forced to conclude that these two sticks do not change length. All right, so even if we're moving relative to each other, we might disagree on delta X, we might disagree on measurements along the direction of our relative motion, but we have to agree on measurements perpendicular to our relative motion. Any questions on that? There's a few things we agree on in relativity. We agree on the speed of light. We agree on our relative velocities, except for a minus sign. And we agree on measurements perpendicular to our relative velocity. Any questions on this? So let's do an example. A lot of examples in relativity involve particles called muons. Muons are nice because on the one hand, they're just like electrons, except that they're 208 times as massive, and they decay with a half-life of 1.52 microseconds. They're nice because they're produced in the upper atmosphere when high energy cosmic rays collide with atoms in the atmosphere. They're also nice because, well, 208 times as massive an electron is pretty heavy, but it's not so heavy that we can't create them with relative ease in the lab. And the fact that their half-life is 1.52 microseconds means that they decay in a reasonable amount of time that we can detect. They're not super short-lived. They don't really serve any purpose. There's no particular reason why the standard model of particle physics needs all of these additional particles. I mean, particle physics, as you'll learn going forward, absolutely requires electrons and quarks and photons and neutrinos and a few other things. There's no particular reason why it needs muons. Frankly, the only thing that muons are really good for is helping us learn relativity. And that's not a joke. Because they decay at a known rate in their own reference frame, we can see what rate they decay at in other reference frames and thereby figure out how much time elapsed in a different reference frame. All right, so 1.52 microseconds. Now, if something only lasts for 1.52 microseconds, 1.52 times 10 to the minus 6 seconds, they move at 3 times 10 to the 8th meters per second. They should only go about 450 meters before half of them decay, because that's a half-life. A half-life is how long you have to wait before half spontaneously decay. And then if you wait 2 half-lives, half of the remaining half will decay. And if you wait 3 half-lives, half of the remaining half decay. So the number that you have present is equal to the number you have initially times 2 to the minus t over 1.52 microseconds, t over the half-life. So if you wait 3 half-lives, you have 2 to the minus 3 fraction left. If you wait 4 half-lives, you have 2 to the minus 4, 1/16. If you wait 5 half-lives, you have 2 to the minus 5, or 1/32 of them left, and so forth. All right, so on average, muons should only travel about 450 meters. But people have done measurements. They've sent detectors up in airplanes or hot air balloons, or they've gone to the top of mountains, and they've checked to see how many muons are detectable up there. And then they check to see how many muons are present on the ground. And let's face it, 450 meters is not that high up. You should see a big difference between the top of a mountain and a lab on the ground, but we don't see a huge difference because these muons are going so fast, all right? And so in their own reference frame, the amount of time that's elapsed is different because a muon traveling at constant velocity, well, you tell me, what kind of time do they measure between when they're created in that collision and when they're detected at the ground? Remember, there's 3 kinds of time: coordinate time, proper time, and space-time interval. Anyone? You can say it out loud. You can type it into the group chat. Somebody must have an answer. What kind of time is observed by a muon or by someone moving at the same speed, moving with the muon? Well, they're present at both events. They're present at their creation. They're present at their detection. And they're moving at constant velocity. So they measure a space-time interval. So if I have a bunch of muons traveling together, half of them will decay when those muons think that 1.52 microseconds have elapsed. We might think that some other amount of time has elapsed. So let's see. Muon is traveling at 0.994 times the speed of light. And we see it travel a distance of 6.36 microseconds, 6.36 times the distance that light travels in a microsecond. So as far as we're concerned, the amount of time that's elapsed is 6.36 microseconds over that velocity, 0.994. So we think that the muon traveled 6.36 microseconds, delta x, and the time delta t equals 6.398 microseconds. So the muon says that delta S, the time between these two events, is the square root of delta t squared minus delta x squared. If we plug that in, we get 0.696 microseconds. So if we naively did this calculation, just using the amount of time we measured, we would say that the fraction of muons remaining should be 2 to the minus this amount of time divided by the half-life, or 5.5%. And that is how many muons would remain if all of those muons had been sitting at rest for 6.398 microseconds. And I just realized I put the wrong delta t up here, but it's not going to matter because 6.36 versus 6.398, I'll fix that later. To the muons, the amount of time that's elapsed is 2 to the minus 0.696 microseconds over 1.52 microseconds. So as far as the muons are concerned, 73% of them should remain. And this means the fast-moving particles can be very long-lived. This is very useful in particle physics. If you want to create subatomic particles and study them, their half-life is how long it takes half of them to decay in their own reference frame. But in your reference frame, a completely different amount of time, a longer time interval might have elapsed. All right. So space-time is weird, right? This delta t squared minus delta x squared is a constant. So if I have an event that happens at t equals 0 and x equals 0, then all of these events at these different t's and x's have the same space-time interval from this event. The space-time interval between an event here and an event here is the same as the space-time interval between an event here and an event here, or an event here, or an event there, or there. All right? So this is a curve showing all the events that have a constant space-time interval from the origin here. This is completely the opposite of the geometry that you're used to. All right? The distance from the origin, if I were to look at in regular geometry, the set of points that are at a constant distance from the origin, I'd get a circle. But in relativity, if I ask not about distance from the origin, but about space-time interval between events, set of all events with constant space-time interval from the origin is a hyperbola. This is the beginning of the idea of curved space-time. It's not actually curved space-time for reasons we'll get to at the end of the semester, but this is the beginning of the idea that geometry of space-time is very different from what you're used to. Any questions? This all makes perfect sense. If this makes perfect sense to you the first time that you hear it, well, congratulations. You all qualify for very high-paying jobs at the Swiss Patent Office. Swiss civil servants, good job security, good pay, good benefits, ironclad banking privacy laws, nice chocolate, nice skiing. You will have to deal with mandatory military service if you're male and you live in Switzerland, but other than that, Switzerland is a good place to go. So you all qualify to work as Swiss patent clerks. All right. So if you have no questions for me, I have some questions for you. So, a person riding a merry-go-round passes very close to a person standing on the ground once and then again. Which person measures a proper time between these two events, and which one measures the space-time interval between those events? So take a moment to think about that, and then I'll show you the answer. And then also, which person measures the coordinate time between those events? Well, they both measure a proper time because they're both present at both events. Anyone who's present at two events, no matter how they're moving in between, measures a proper time. That's why I hate the word proper. Proper implies something official and agreed upon, but everybody measures a proper time. There's nothing particularly proper about it. The space-time interval is measured by the person standing on the ground because that person's in an inertial reference frame. The person on the merry-go-round is not in an inertial reference frame. We know this because their velocity is changing. You might say, well, according to themselves, their velocity isn't changing. No, their velocity, they don't measure their own velocity as changing. But if they let go of something, they feel it accelerate away from them. Think about when you're on spinning rides. It feels like everything's being thrown back against the walls of the ride. Now, the person on the ground also measures a coordinate time because they're in an inertial reference frame. All right, another question. A spaceship departs from the solar system, goes at constant velocity to a distant star, gets to the distant star, realizes that they left their paperwork and so they can't actually go through the immigration checkpoint at that distant star. Instead, they return to Earth to get their paperwork. They arrive back at Earth at event B. Which kind or kinds of time will they measure between those two events? A proper time, a coordinate time, space-time interval, two of those, all of those. They measure a proper time because they're present at both events. They can't measure a coordinate time because they're not in an inertial reference frame. Their velocity changes. You might say again, well, according to them, their velocity doesn't change. Yeah, but when the ship changes direction, they feel those thrusters change the velocity of the ship. Just like when you're in a car that's accelerating, you get thrown back against the seat. And when the car comes to a stop, you jerk forward. That's the sign that you're not in an inertial reference frame. Skip that one. Okay, now we have to think about the formula for space-time interval. The space-time interval can never be larger than the coordinate time. True or false? Think about the formula, maybe write it down. Delta S squared is delta T squared, the coordinate time, minus squared distance between the two events. Delta S squared could be equal to delta T squared if this is 0, if this distance between the events is 0. But it can never be larger because the squared distance is always going to be non-negative. You may be thinking, wait, is that still true in relativity? We've used imaginary numbers elsewhere in physics. We have used imaginary numbers elsewhere in physics, but not here. And even when we used imaginary numbers, remember that in the end, we always took the real part. Okay. So two events occur 5 seconds, 5 light seconds, 5 seconds apart in time, and 3 light seconds apart in space. All right, that's what we measure. We're in some inertial reference frame, and we say, hey, they are 5 seconds apart in time and 3 seconds apart in space. But someone else is going at constant velocity and manages to be present at both events. So what time interval do they measure between the events? Take a moment to calculate that, and then we'll discuss. 4 seconds, because delta S squared is going to be 5 squared minus 3 squared, which is 25, minus 9, which is 16. That's the square of 4. 3, 4, 5 combos show up a lot in relativity because they're convenient. They're just like Pythagorean triples. Okay, now, what is the space-time interval between events A and B in this diagram? What about between A and C? You know what, let's just find the space-time interval between A and all of these events. Find the space-time interval between A and B, A and C, and A and D. Okay, between A and B, it's just 4 seconds because delta t squared, well, delta t is 4, delta x is 0. They both happen at the same position in space. Now between A and C, well, delta t is 5, delta x is 3, so you get 5 squared minus 3 squared, or 25 minus 9, or 16, which is the square of 4. A and D, let's see here, delta t is 3. Delta x is minus 3. So 3 squared minus 3 squared, 9 minus 9 is 0. So the space-time interval between A and D is 0. Now, you tell me, how fast was something traveling between event A and event D? Anyone? Type it into the chat if you don't want to say it out loud. Well, the distance delta x is minus 3. And the time delta t is 3. So delta x over delta t is minus 3 over 3, or minus 1. So this is going at light speed. So to light, the space-time interval between two events is 0. As far as light is concerned, all events that light can be present at both of, all events have 0 space-time interval between them. Light has never seen time elapse. As far as light is concerned, the universe was just born. What time is it? 10:46 in my reference frame. One more. Which space-time interval is larger? The interval between event O and event A, or between O and B, or do they have the same space-time interval, or is there insufficient information? And yes, technically D, because technically, you know, unless we do this, well, unless we, you could always argue that technically we haven't measured any of it, but come on. Without taking a ruler to the screen, you should be able to figure out. So I'll tell you it's not D, it's either A, B, or C. This is the largest space-time interval from O to A. Now you may be thinking, but wait, the largest distance on the diagram is from O to B. Yeah, but space-time interval isn't a distance on the diagram. Space-time interval is delta t squared minus delta x squared. Delta t, delta x. Delta t is the same in both cases. Delta x is larger for event B, so we're subtracting a larger thing from delta t squared when we look at event B. So we wind up with a smaller space-time interval. Any questions? Anyone? Anyone? Going once, going twice.
So if it's closer to 1, it means it's less. Like, because the distance from delta x and delta t squared is going to be closer to 1, which is the same as light.
Nobody said that the distance has to be 1 or closer to 1.
Because for light, you get the space-time interval is 0.
Oh, if the speed is closer to 1. Basically, the faster you travel between two events, the faster you're traveling, the smaller the space-time interval you're probably going to measure.
Mm-hmm.
But yeah, if you're along a speed will definitely change the space-time interval. But basically, if I'm comparing two events with the same time, with the same coordinate time between them, then the ones that are separated by the larger distance will have the smaller space-time interval.
Okay.
Other questions? All right, so let's quickly do the twins paradox, one of the most famous paradoxes in relativity. We've got two twins. They start off on Earth. One of them decides to become an astronaut and go to Alpha Centauri. The other one really doesn't feel like getting in shape for astronaut training, so they stay on Earth. Now, the one who goes to Alpha Centauri only stays there for a very short time before coming back. The one who's on Earth, well, they never move at any significant speed or distance. So the space-time interval from here to here could be calculated, and the space-time interval from here to here could be calculated. Alpha Centauri is 4.3 light years away. It takes them 6.5 years to get there, so we can figure out their speed. It's 0.66 times the speed of light. And so we can figure out the space-time interval from here to here. We say that 4.87 years elapsed on the ship going from here to here. Another 4.87 years elapsed on the ship going from here to here. Meanwhile, 13 years elapsed on Earth. So these two twins started off looking the same. And yet, when the first twin comes back, when the one who went to Alpha Centauri returns to Earth, they're younger. Now, many people look at relativity and they think about these diagrams of light arriving and they say, oh, well, it looks like less time passed, or it looks like different amounts of time passed in these different scenarios because, it took the light longer to get from one person to the other, or you look at the way light's traveling between things. So it just looks like time is passing. It's like a movie that got slowed down or sped up. But no, it's not just that things look different. It's not just that you make a movie and things look different. Time is actually different, right? The person on the ship, it's not like they looked at Earth and said, wow, Earth looks weird. I'm getting these distorted images from the light that's arriving too quickly or too slowly. It's not that. It's that time was literally different. Every chemical reaction in their body elapsed as though 4.87 years had gone from here to there, and then another 4.87 years. Every chemical reaction that results in aging proceeded as though only 4.87 years had elapsed on each leg of the trip. Okay? Every chemical reaction in their brain that produces consciousness and the perception of events elapsed as though each leg of the trip took 4.87 years. Everything that they experience, every bit of chemistry and biology in their bodies is as though 4.87 years elapsed on each leg of the trip. Okay, that is really the time that elapsed for every single process on there. Any questions on that? There's one other thing. Why this? Some people call this a paradox because they started off at the same age, looking the same, and now one of them has aged more than the other. There's another reason why it's considered a paradox. According to the person on Earth, the person on the ship was traveling at 2/3 the speed of light. But according to the person on the ship, the person on Earth is traveling away from them at 2/3 the speed of light. So it'd be very tempting to say, hey, according to the person on the ship, 4.87 years elapsed, but we could do a calculation to figure out how much time elapsed to the person on Earth, and surely that person on Earth must have seen an even shorter amount of time, right? We could just use the definition of space-time interval to compute how much time elapsed on Earth using whatever delta t the person on the ship measured and whatever delta x the person on the ship measured. Why can't we use the traveler's measurements of delta t and delta x to compute the space-time interval? What's our assumption about the values of delta t and delta x used to compute the space-time interval? What's our assumption about the reference frame in which those numbers are measured? We assume that those numbers are measured in an inertial frame. Now you tell me, is the person on the ship in an inertial frame? Does their ship change velocity? I hope your answer is yes, their ship changes velocity, which means that they're not in an inertial frame. All right, that's all we have time for. On Friday morning at 10 a.m., the midterm will be available to you on Blackboard. You should download it. You'll have until noon to complete it and scan it and upload it and get it back to me. I'll have it graded sometime this weekend. Then on Monday, we're going to continue doing a little bit more with the space-time interval and then talk about calculating proper time. Have a good day.